If a verification layer lives inside the same harness as KAIROS, the harness can consolidate the verification records too. And inside the harness verification layer cannot verify the harness. This is not a failure mode. It is a structural property. The only exit is a referent that lives outside both the model and the harness. Te Pono V.E.R.A is built on that principle. But if you wanted to verify KAIROS's consolidation, what external referent would you need and where would it live?
Let's get into it.
This is the Hamberger Report. I'm Andreas Hamberger, Enterprise Architect and AI Governance Researcher. Wellington, Episode 15 of Real Intelligent AI, V.E.R.A. On 31st March 2026, a packaging error in Claude Code exposed approximately 512,000 lines of unobfuscated source code to anyone who looked. Independent analysis from multiple technology journalists converged on one structural finding. The model itself is no longer the competitive position in production AI systems. The orchestration layer means the harness, the code that manages agent context, coordinates parallel work streams, handles memory and persistence, and governs agent behavior at a level below the API. The model is available to anyone with an API key. The harness is what separates production AI systems that work reliably from those that do not. 84,000 GitHub stars and 41,500 forks accumulated before takedown notices arrived. Anthropic confirmed the release was caused by human error, not a security breach. But there is a second implication. The post-leak commentary did not make explicit. If the harness is the moat, the harness is also the failure surface. An agent that reasons incorrectly can do so at the orchestration layer when managing context, consolidating memory, or deciding what prior observations to carry forward. The leaked codebase exposed 44 hidden feature flags for unreleased capabilities. 3 are directly relevant to the verification argument in this episode. The first is KAIROS, an autonomous daemon mode that operates in the background while you are idle. KAIROS maintains daily logs and performs memory consolidation, merging observations, removing logical contradictions, and converting vague insights into absolute facts. It operates on a 15-second blocking budget invisible to the user. Episode 12 introduced the E-type and N-type distinction. E-type claims assert that something exists and require external source verification. N-type claims follow from logical structure and do not. KAIROS performs automated E-type to N-type transformation while you are idle. It converts something uncertain to something certain. No external verification is involved. The transformation is internal to the harness. If a verification layer lives in the same harness as KAIROS, it is subject to the same consolidation process. That layer's own records could be reframed or treated as absolute fact by the same daemon. And inside the harness verification layer cannot verify the harness. This is not a failure mode. It is a structural property of verification. The structural property has a long history outside AI. Hardware security verification faces the identical problem. A 2026 research preprint notes that AI systems are simultaneously the verification tool and the verification target. The recursion is the same. You cannot use a system to verify itself without an independent referent. This is not a limitation of current AI systems. It is a principle in formal verification theory. A proof checker that is itself unverified provides a weaker guarantee than the proof it checks. Ken Thompson identified this principle for software in 1984. The same constraint applies to AI agents running KAIROS-style consolidation today. Episodes 12 through 14 approach the same underlying problem from 3 angles: claim extraction, confidence calibration, and governance vocabulary. This episode is the architectural extension. Even if you address confidence calibration at the model layer and claim type classification at the evidential layer, you still face the recursive verification problem at the harness layer. The object under test and the test instrument cannot be the same object. External positioning is the structural requirement, not a design preference. Te Pono V.E.R.A's NTP-derived checks compare AI reasoning outputs against canonical reference that exist outside both the model and the harness. 4 verification frameworks emerged from the post-leak commentary. Each addresses a different layer and a production AI governance framework may need more than one. Precise positioning matters here because conflating these categories does not help organizations identify what they actually need. PRISM measures statistical consistency. Does the model return the same answer when asked twice? A model that consistently returns the same wrong answer scores well on PRISM. It would fail Ve.E.R.A's logical grounding check. Consistency is a necessary condition. It is not sufficient. The Proofpoint Agent Integrity Framework addresses behavioral monitoring. What is the agent doing in real time? Intent detection, action auditing, anomaly flagging. This complements Ve.E.R.A at a different architectural layer. Behavioral monitoring tells you what the agent is doing. Logical grounding verification tells you whether what the agent claims follows from what it should know. Ensemble verification checks agreement across models. Agreement is not truth. Models trained on similar data with similar objective functions can agree on the same wrong answer. Ensemble agreement validates consistency. It does not validate correctness. Ve.E.R.A addresses a different question. Is this claim logically grounded? Does it trace to a verified external referent? The Crampits analyzer classifies each claim under the NTP E-type and N-type distinction. Neither check depends on the model's internal state or the harness's consolidation history. New Zealand's privacy law changed on 1st May 2026. The indirect collection obligation now creates a specific immediate verification requirement for every organization running AI agents in this country. An AI agent that collects personal information indirectly, including through harness-level memory consolidation of conversations and inferred attributes, creates an E-type claim requirement, which data was accessed, from which source for what stated purpose. That claim must be demonstrable to the individual. If the agent's reasoning about its own data access is not externally verifiable, demonstrating compliance becomes structurally impossible. You cannot audit KAIROS-style consolidation through the API output. The consolidation is below the API surface, inside the harness. A compliance record subject to the same consolidation process does not provide the independent audit trail required. New Zealand's National Cybersecurity Advisory Body, following the Claude Code disclosure, reinforced this at the supply chain layer. Verify every AI tooling source against official vendor channels only. A concurrent supply chain attack against a widely used JavaScript package ran within the same window. 3 separate contexts. 1 structural principle, logical verification, privacy compliance, and supply chain security all require external reference. 1st May 2026 makes that explicit for AI agents in New Zealand. This is where the architecture and the coding arc connect. Te Pono V.E.R.A is designed to position the verification layer where KAIROS cannot reach it. The referents are external. The verification does not depend on the model's internal state or the harness's memory consolidation. This is a deliberate architectural choice specified in the V.E.R.A Logic Engine Phase A architecture vision. The Claude Code leak validates that choice from outside the system. The Crampits analyzer is operational, all tests passing. The formula parser is operational, 15 tests passing. The e-verification service has its architecture defined. The proof of concept queries Wikipedia and Wikidata as external canonical sources. The D-service architecture is defined. The open problem is claim extraction. Before you can verify a claim, you have to extract it from generated text. That extraction process is subject to the same failure modes as generation itself. This is the hardest unsolved problem in the V.E.R.A Logic Engine's development. The coding arc in this series is where that work happens in public. If you are building verification infrastructure for production AI systems, the architecture is open for scrutiny, challenge, and contribution. The full source is on GitHub, under GPL 3.0. KI consolidates observations and converts vague insights into absolute facts while you are idle. This series documents Te Pono V.E.R.A as the work happens in public. The architecture is open source. The problem is structural. The recursion is real. The principle the coding arc demonstrates is architectural, not theoretical. External referents are not a performance optimization. They are a governance requirement, and New Zealand's indirect collection obligation that took effect on 1st May 2026 makes that explicit. Logical structure is this: if the harness consolidates claims and the verification layer is inside the harness, then the verification layer cannot independently audit the consolidation. The only exit from that recursion is a referent that lives outside both V.E.R.A's NTP-derived logical checks. Compare AI reasoning outputs against canonical referents that exist outside the model and outside the harness. The object under test and the test instrument are not the same object. The full source is available on GitHub under GPL 3.0. If you wanted to verify that KAIROS's consolidation was logically grounded, not merely consistent, what external referent would you need and where would it live?
That is the Hamberger Report for today. If this was useful, subscribe and hit the like button. It helps more professionals find the channel. You will find links to everything we covered in the description below. I am Andreas Hamberger, and I will see you tomorrow.
Like and subscribe.